Good morning, everyone. Good morning, Christian, who is joining us from East Coast America. Good afternoon, everyone in EMEA. So for a new session, which will be deep knowledge and actionable. And this is a presentation by Dr. Cristian Soto, who's Chief Operation Officer and Vice President of Research and Development at Fluitec. And his topic is correlation between MPC and the ruler in between under laboratory oxidative conditions. Thank you, Christian. The floor is yours, and I can't wait to hear all you have to say.
Great. Thank you very much, Guillaume. We're going to get started right away. So the objective of this work was the aim is to explore the orthodoxy of antioxidants that are meant to extend the life of an oil and therefore antioxidant rotation indication of remaining life. To do so, we're going to be putting this orthodoxy to the test by monitoring oxidation processes using an accelerated testing equipment called the TOPP, and we will be monitoring various parameters such as remaining useful life of antioxidants, RPBOT, and total acid number. And we will see how these characteristics of the oil correlate to actual varnish formation by looking at MPC and deposit evaluation strategies. The aim here is to gain additional knowledge regarding the quantification of remaining useful life, not only in terms of antioxidants, but in terms of the lubricant itself, condition monitoring strategies, for example, sensors, and making life decisions for the lubricant. All right, a little background, and we'll move quick through the background as most of you are probably familiar with most of this subject. So oxidation clearly produces harmful effects to base oils, and this happens through the formation of reaction products. And we will be taking a deeper dive on that. The reaction products can impart, have an impact, a negative impact on a variety of performance specifications, such as foaming, demossability, deposit formation. In particularly, we will be focusing in this presentation. Now, the ways to monitor oxidation that we will be speaking about today are ruler, RPBOT, and TAN. FTIR we will leave for another time. Antioxidants. So since oxidation is a bad actor, a bad process for the life of the lubricants, lubricants are formulated with antioxidants, and clearly they are added to the formulations to reduce the negative effects of oxidation. Antioxidants are sacrificial in nature and basically work by getting preferentially oxidized over the oil that they're intending to protect. In this process, they don't just, of course, disappear. They transform, and they transform into stable free radicals and other species, as opposed to very active free radicals, which are formed when they are absent. The reactivity and solubility of the byproducts of antioxidant oxidation are just as crucial as the byproducts of the oxidation of oil itself. And this I'm speaking about especially in terms of deposit formation and other functional parameters of the lubricant. Therefore, tank-side antioxidant packages or feed and bleed programs, which are meant to extend the life of the oil, need to be selected carefully in order not to have actually deleterious effects due to incompatibility primarily, but they, as these incompatibilities may work against the overall performance of the lubricant. So let's talk a little bit about some aspects of oxidation which will be relevant later into our presentation. So there's many different ways of looking at oxidation. I like looking at it in this manner I'm presenting. So in essence, the RH in this set of equations represent the lubricant, which upon heat and presence of oxygen and or water will form free radicals of the hydrocarbon and also peroxy radicals. There could also be, under the right thermal conditions, breakage of the carbon-carbon bonds of the chain, the main chain of the oil molecules, and resulting in two radicals. These radicals then interact with oxygen, forming a peroxy radical. Peroxy radicals then will interact with oil molecules again and make peroxide and creating a radical. Now, this propagation step basically allows to continue to form peroxy radicals, which will continue to attack the oil if not mitigated. And that's the role of primary antioxidants, to break this step of the reaction. Now, upon further heating, once these peroxy radicals are formed, a lot more things can happen, as peroxide itself can decompose into alkoxy and hydroxy radicals, and this can then yield a variety of different reaction products such as alcohol, aldehydes, and ketones. Upon further heating, you will be able to also generate fatty acids at higher temperatures. Typically, this is expected to be at higher than 120 degrees. However, we commonly encounter them below that, and that's likely due to the presence of other agents such as catalysts present in the reaction. These fatty acids and esters that can be formed then can further polymerize, leading to actual varnish formation on the critical components of the equipment. Now, keep in mind that one of the big values of the antioxidants is that one antioxidant can neutralize, say, 4 radicals at low temperature, but at high temperature, they can be much more effective and neutralize up to 40 radicals. So this is one of their big values, that they're not acting one-to-one for each radical, peroxy radical form, but actually are able to neutralize stoichiometrically many more free radicals formed per molecule of antioxidant. In summary, you can see here the hydrocarbon oil is first oxidized and generates as alcohol, aldehydes, and ketones, and then upon further oxidation, the formation of carboxylic acid, which often may be encountered in applications such as turbine oils. That was just a previous background. An additional background is, how are we defining the end of life in terms of oxidation? An ASTM has several definitions. In terms of the ruler is when 25% of the antioxidants remain. RPBOT is when less than 25%, less than 25% of the original value. And in the case of TAN, total acid number, is when there is an increase of greater than 0.3 milligrams of KOH. And ASTM, although that's 7843 for MPC, does not define end of life, but rather that the lubricant is in critical conditions at a DE greater than 30. So we'll explore these limits or these warnings, and rather whether they are sensitive enough to help monitor the condition of the oil and thus manage the life of the lubricant. All right, so some experimental results that then will be followed with some insights and conclusions. So TOPP basically is an accelerated test where there is a use of a catalyst and air is bubbled through the lubricant at 120 degrees C. In our examples here provided, we will be looking at the results after testing 14 commercial oils, which I believe is a good number. We've done many more, but this is a good number to get to some conclusions. The acid number, monitoring of this experimentation. So as we mentioned, we looked at a number of lubricants and for 12 weeks, and the results here for the acid number are shown. As we can see, at 120 degrees, not much acidification took place in most of the lubricants. However, number 5 and number 13 do show a significant acidification. In fact, after 12 weeks, they went above and beyond the 0.3 milligrams of KOH increase. It's important to note that lubricants, for example, 2 and 14, start out quite acidic and do not increase in acidification significantly enough to reach critical conditions. That is coming from primarily additive packages, and in some cases, some of them are quite acidic themselves from the starting point. So what happens when we increase the temperature to 180 degrees C to explore if one could further predict the behavior of oils by going at a higher temperature and perhaps accelerating the process? We can see from the results here that when we go to 180 degrees C, as highlighted right here, we see many different lubricants actually showing really significant acidification. In fact, some of them are different than those that were presented at 120 degrees that did not show acidification under those conditions. So what does this mean? And in fact, several of them exceed the results of those of lubricant 5, such as lubricant 6, among others. So why is this happening? Well, the options here are that there is different reaction pathways being open at higher temperatures, meaning that experimentation at 180 degrees is not just an acceleration of 120 degrees, but an entirely different reaction pathways are opening up. And we will now look at an MPC for the same group of lubricants. We can see that there is many more additives showing actual reaction happening at 120 degrees, and unlike what we saw for acid number. We also see that several formulations, especially these two we're to highlight, actually show an increase in MPC followed by a drop to then increase again. This may be due to precipitation happening, where some of the products being made come out of solution, drop out, causing a drop on the MPC, and then to continue to grow again. If we compare this to acid number, we can just more visually show that many of these lubricants that did not show acidification do show an increase in MPC value, indicating that at 120 degrees, we're having, in many cases, oxidative chemistry perhaps taking place, but not sufficiently to be generating acid number, an increase in acid. At the same time, we're going to tabulate here how many and which lubricants are reaching critical condition. And this will be useful for us later. No need to memorize it. Then when we look at MPC and we compare it between 120 degrees at the highest value reached rather than the total length of time, as we saw some maximums on the MPC being reached before the 12-week period. When we compare those values, we see once again that at 180 degrees, we're finding results of compounds that are generating higher MPC values than those at 120, clearly, and the order of these are different, correct? So lubricants, for example, 7, 8, 6 show very high MPC, while at 120, they're among the lowest. If we compare this to acid number, once again, we can see that those lubricants that are reaching sometimes very high MPCs are not necessarily getting significantly acidified. This indicates that some of the components being made that are contributing to MPC are not always necessarily acidic in nature. Now, what else can we surmise from this is that, once again, different reaction pathways open up at 180 degrees compared to those at 120. Worthwhile mentioning that 180 degrees is temperature well exceeding those of what is typically encountered in the turbine operations. Looking a little farther at the MPC, and we see here that a number of them are reaching a critical value of 30, which is from basically lubricant number 9, 10, 11, 12, and 13. After, and this is the highest value, correct, from the testing, not the 12-week value, but the highest value. And we're also showing, for reference, a line here showing the 20 DE value for MPC. So here we compare actually against what was observed on the test tubes where these tests are conducted. We can see that there is a pretty good correlation that after above anything over 30, there is a significant number of deposits. However, the relative ranking is not always simple. We can see, for example, number 13 showing a slightly less deposits, yet the highest MPC as an example. But overall, there is a fairly good correlation between the MPC and the TOPP tubes in terms of deposits. And we can also go farther and extend down to the tube at number 6, which is a delta E of about 20, where it's already showing some deposits, and we'll speak more about this in just a bit. So now, if we want to also look at not only MPC and acid number, and we also want to look at ruler and RPBOT, and then look at how these compare to MPC, we can look at the average value of the lubricants shown. So here we see as the ruler drops in the blue line and the RPBOT drop in the orange line, we see an increase on the MPC value. This makes perfectly good sense. This is kind of one would expect. However, keep in mind that these are average values. We also notice that the ruler is showing a more pronounced response to oxidation than RPBOT, once again, on average. As the ruler response proceeds over in terms of weeks of oxidation, we can see that the concentration of antioxidants reduced, the rate of the remaining quantity begins to flatten out. And this is consistent with what one would expect with first or second order reactions. RPBOT includes other factors such as the base oil, for example, and not just the antioxidants. And it appears that some of these other factors also may blunt the response of RPBOT to oxidation, again, on average. And here we're just showing what the critical value is for the MPC. And as you can see, we would argue that on average, we're not reaching critical conditions under these test conditions. And in terms of ruler and RPBOT, again, we don't really reach critical levels, and this is on average. So, however, the picture changes very, very much once we start looking individual oils. And we can see that there is many, lubricants reaching critical condition. These are captured in the upper part. And the same for RPBOT, we have one reaching critical condition. But you can see the enormous spread that develops as the experimentation goes forward. You see a variation that is quite impressive. So what's happening? Why are these things happening? By the way, at 180 degrees, there is no antioxidants left, and the RPBOT is also down to 0. So That's just written here for reference in these images. All the results here are for 120 degrees C. Now, so one would expect? One would expect to be able to predict, according to our orthodoxy, that as ruler goes down, and our PVT goes down, and tan goes up, one would expect perhaps deposit formation. That's one of the reasons one is putting antioxidants into the system or formulating in order to reduce the formation of deposits. But what in fact happens is that if we were to look at these, we should be able to say, well, we will be able to predict which lubricants are the ones that are generating the most deposits. And we saw that on average, that would be a reasonable thing to expect. However, what in fact happens is that what the prediction is not very good by looking at ruler or RPVOT, but we do see that MPC has a good correlation with deposit formation, as perhaps one would expect. And if we were to extend it down to a delta E of 20, it would include the lubricant 6, 7, and 8 as well, which is possibly a reasonable thing to expect, since we see already some deposit formation in lubricant number 6. So why does this happen? This happens due to complexity, and the complexity is driven by, as we saw, oxidation, but also the complexity brought about by antioxidant action, which brings additional level of complexity. The reaction mechanisms of antioxidants are here described. One can look at the reaction rate and the equation, which includes a K factor. This is constant, and this is basically the Arrhenius equation, which shows the dependence of temperature. The rate also depends on the concentration of antioxidant and peroxide radicals. So the energy of activation in this equation is basically what controls the different reaction pathways. As an example of that, I can show here one where there is an energy activation going to one product and an energy activation going to a second product. As an example, depending on the temperature, we may get one or the other product. There's a lot more details to this, but it's just a visual on how these reaction pathways operate. Okay, summary. So the reaction chemistry of different lubricants can yield very different products and different rates of consumption of antioxidants. And this is consistent with the fact that there is many different additives and base oils and different operation temperatures for the different systems. So in practice, one can see really a wide variety of different compounds being formed. The reactions at 120 and 180 can follow different reaction pathways, and this can be explained also many of the differences observed between 120 and 180 data presented. We did not focus a lot on this, but it's indirectly through MPC measurements, we can see that although in some systems the antioxidants are depleted quickly and RPVOT as well, yet the MPC values remain relatively low. That's due to the solubility characteristics of the mixtures. This solubility can really prevent prevent the deposition by being able to increase the solvency power of the overall mixture. This does not suggest the presentation that antioxidants should not be used. They are effective and cost-effective, and we don't expect that solubility enhancement alone can become a way for extending the useful life of oil in terms of deposits. As we saw, there is clearly a trend on average of and the benefits of having antioxidants in action. Lubricant formulations have changed over the years. The antioxidants even to critical levels, have only, as I mentioned, a qualitative relationship to MPC, and the ruler helps to detect this consumption early. It is it may be also worthwhile to highlight that to separate causes and effects, and to try to define the lubricant, it is the opinion of this author, that the lubricant end of life may be best defined by performance characteristics or the effects rather than the causes, and those should be grouped perhaps separately. These causes can be used to certainly monitor the system rather than to define life end of life. One tool that we often use historically has been the asset number, and perhaps this number needs to be reduced. As you saw, even at 120 degrees, we don't typically see significant acidification, and it's recommended that this number may be reduced to 0.1 milligrams KOH. TAN and RPBOT are meant to be used as leading indicators, but oxidation monitoring for individual lubricants do not have a strong enough predicting correlation to individual formulations, and we saw that MPC does show a stronger correlation. It is proposed also in this presentation that the MPC critical level be dropped to 20 DE, as we see in many cases that the MPC level can be quite low, and one can still be detecting the formation of deposits. Now, most importantly, I think the takeaway from this presentation is that the low correlations between our current monitoring strategies to deposit formations hints that we are still in need of a method or methods where a better predictability of deposit formation can be established. I'd like to thank everyone in my team in operations and R&D of Fluitec, with whose support this presentation would not be possible. Thank you for your attention.
Thank you so much, Cristian. So this is so dense and rich. I'll confess to you that I'll probably need to find half an hour to re-listen to the recording to take it all in. We have little time now. We have a question from Alessandro asking the topic you started covering. Is the 25 limit for ruler and RPVOT actually too low? What's your thinking about this?
I think it's something that we, by looking at not only our data, but the overall industry and laboratories and further discussion, I think it's definitely something that needs to be looked into. So very, very good point. This seems to indicate that that may be the case, but most importantly, is there this strong enough correlation between ruler and RPVOT and deposit formation, and that correlation is a little weak. So simply increasing the limit may not be sufficient to improve that correlation.
Okay, we have too many very good questions. We have one from Tanaraj asking, phenols are sometimes not stabilizing compared to amines. And some turbine oils have phenolic and don't have phenolic. Do you wish to comment on that, the relationship between the two and the formulations?
I can make a quick comment. So not all phenols are created equal. There are formulations that operate fairly well based on phenolic antioxidants alone. And there are formulations with amines that are without phenols that are operating quite effectively. And then there are formulations with both antioxidants present. So it a lot depends on the choice of antioxidant for the particular oil that has been developed. And so testing is required, and not simply kind of a wholesale assumption that, you know, phenols are kind of a lower temperature and means higher temperature, or all this type of discussion. But
Thank you,
look at
Cristian.
individual packages. Go
We've
ahead.
reached the time. We have more questions we'll have to take offline, but thank you so much. Really impressive. And all right.
If you send this to me with questions, I'll be happy to answer them.
Very good. Goodbye.
Very good. Thank you so much. Thanks everybody for your time. Bye-bye.